Hey, good evening, everyone. This is Celso Batalha and Astro 10 course. I'm here in the observatory and initiating the chat room early today as we have a workshop going on again. So, um, and so let me see. I start sharing my screen. And today is the last week of class. Today is the last week of class, and as you know, tomorrow we have, in fact, today we are having a makeup exam, and you can try to do it. And I'm also have all homeworks. I mean, the homework quiz, not the discussions. Discussion, they are closed, and I cannot review and try to open again because I will not have time to read all the posts. So see, we have 50 students, right? So several discussions, 5 of them or 6, and it's just impossible. So that's why we do every week at a time. But the homeworks are opened, and makeup exam is still available up to midnight tonight, and I'm having the final exam scheduled for Thursday at 5 o'clock in SA 114, and that is in the New Science Building. But some of you are trying to do the exam earlier. You can, but you have to communicate with me so that I can be prepared with the exam and give it to you. So today I would like to go over measuring galaxies, and I have here some slides, and it's pretty much a continuation of what I talked to some of you. In fact, can I move this away? No, probably not. Let me see if I can take this away. Nice if I could put thing here and I can annotate. That's cool. There you go. But in measuring galaxies, the main point is to introduce the types of galaxies that exist out there in space. And as mentioned previously, by studying galaxies, we have some idea of how the universe in large scale is organized, what sort of structures exist, and what sort of energy happen to be controlling and guiding the dynamics of galaxies. So one of the points that are going to pop up as we move through those slides is that galaxies, especially the big ones, not the dwarf smaller galaxies, but galaxies in general, they come with different type of morphology, but more than that, they have a supermass black hole in their very center part, in their very core, and they are also surrounded by dark matter. And those two parts are very important. Dark matter and black holes in the core of galaxies are important components of this particular chapter. So if you think about the universe in large scale, there are two things going on. One is the universe is homogeneous. What does it mean? I mean, you look at it and say, hey, how can it be homogeneous if I have a sun and planets and then you have stars? I mean, it's not homogeneous. Homogeneous being is the same all over. And of course, there are differences between stars and planets. And if you look at the galaxy itself, it has different components. That's true. So the universe is homogeneous if you take if you take a large scoop of it over several mega light years. and then you analyze the content of this group, and it's basically the same no matter which part of the universe you collect. So of course we haven't visited the entire universe, this is impossible, but based on what we observe, it seems the universe is homogeneous. It seems to be in average the same everywhere. So there is not a point in the universe that happen to be um, different from the rest. So in that sense, in large scale, the universe is homogeneous. If you go to the smaller scale, this is not necessarily true. Now, what is isotropic means? So the universe is isotropic in the sense that if you look in any direction, right? If you look in any direction, you will, um, it's gonna appear to be the same no matter which direction you look. So the universe seems to be both. So it's homogeneous in the sense that it appears to be the same all over, and also is isotropic in the sense that you can look in any given direction and the universe appears to be the same. So what's the basic definition of galaxies? Again, galaxies, the last step in our course Introduction to Astronomy, and it indicates the biggest structure there is. So bigger than galaxies is group of galaxies, right? So it's not something different. It's a group of galaxies. You put a bunch of, like human beings, right? One human beings. So what is more than one human beings? Okay, 10 of us, right, together. So galaxies are the less structure there is in the universe as we know. And bigger than that is clusters of galaxies or superclusters of galaxies. So exactly what this unit is. So galaxy is a group of stars and dust that happen to be bound by gravitational force. That's what keeps galaxies together. And even if you think about galaxies in different locations, so in different parts of a local group of galaxies, they are also bound gravitationally. Now, our local group of galaxies that consists of a few dozens of galaxies, two of them, the biggest one, are our Milky Way and Andromeda galaxies. They have gravitational interaction. So they are bound in the sense that the smaller galaxies that happen to orbit our Milky Way and Andromeda, they are called satellite galaxies. They are, in no time, they will be part, they will observe, they will be a part of a major system consisting primarily of these two major galaxies, Andromeda and Milky Way. And since gravity is so efficient in this and governing the local group of galaxies, eventually both Milky Way and Andromeda will merge in a few billion years. So gravity controls and guide and govern the dynamics of galaxies in local groups. And what we are going to see later on is that when you go to large scale, not the scale of a local group of galaxies, but in the scale of super clusters of galaxies. So although gravity keeps them together, but dark energy that controls if you will, the energy in voids around which the superclusters of galaxies happen to be located. So dark energy is the one responsible for giving the last word. And the last word is the universe is expanding, accelerating as we speak. So how do we classify galaxies? So the classification of galaxies by their morphology doesn't have any correlation with galactic evolution. So when we see galaxies displayed in different forms, so it doesn't mean that a spiral galaxy become an elliptical or elliptical become a galaxy or spiral or irregulars happen to be put together to form some of them. So galaxies are classified based on their appearances. So, and then you have primarily spiral galaxies, those that appears in the right-hand side of this image here, and elliptical galaxies that happen to have an elliptical shape. In fact, all these galaxies that appear in these pictures, they are pretty much spiral galaxies. And you can tell they are spiral because of these dark lanes that go across their spiral region, which indicates the presence of dust. So spiral galaxies, those that show themselves with spiral arms, are classified in spiral A, B, and C, depending on the ratio of the size of their bulge to this dimension itself of the galaxy. So spiral A are those in which the bulge are the largest component, and the spiral arms seems to be tightly wound around the bulge. So uh, the galaxy in the middle here, sombrero, on the left-hand side, is one example of such a type of galaxy. And SC are those that are, on the contrary, the bulge, the central bright part, happen to be smaller when compared with the dimension of the galaxy itself. And the spiral arms are open up. They are not tightly bound around the bulge. And the other type of galaxy is so-called elliptical. And then you can see in this tuning fork diagram, the elliptical galaxy divided among E0, which are those that appears to be an elliptical, but they are almost spherical in shape. And E7, they are also elliptical, but they are elongated. So the number 0 to 7 is an integer number. 0, 1, 2, 3, 4, 5, 6, 7 is an integer number that qualify the flatness of the galaxy. And the other group, so we saw the spirals, we saw the elliptical, and the last group is the so-called irregular galaxies. They don't have any particular shapes. So when you look at these three different groups of galaxies, elliptical, spirals, and irregular, keep in mind, we are talking about hundreds of billions of stars in most of them, right? And in addition to the stars themselves, think about the host of planets and satellites they have. Think about, in the case of spiral galaxies, the amount of dust they contain. Irregular galaxies, they might range over 50% of their material is pretty much dust. So they are still forming stars as well as spiral galaxies are. Elliptical galaxies do not form stars anymore because their star formation rates are pretty much done. So one of the major difference between spirals and ellipticals is in the process of star formation. So spirals are pretty much forming stars, and elliptical are not. They are done. They are pretty much unfertile, if you will. Again, SBA, B stands for bar, like a, let me move this. Oh, I cannot move this. It's funny. There you go. I got it there. Let's see if I can. No, I cannot. Oh, there you go. I could. So bar, let me go back. There you go. So SB, this capital B stands for bar-like structure. In the tuning fork diagram, the spiral galaxies that happen to be in the right-hand side of the tuning fork, they are spiral barred galaxies. And then you can see in the diagram or in the illustration, they have a kind of a line, a bar, or a rod. In fact, it's a rod of stars that goes across their bulge. So those are the spiral barred galaxies. And they are divided in A, B, or C, depending on how large the bulge is when compared with the opening and the size of the spiral arms. So S0 are a kind of an interface, if you will, between the elliptical and the spiral. So S0 are the spiral that they do have a disk and around the bulge, but it doesn't seem to show arms, spiral structure. Um, so how is it that the shapes of the galaxies are maintained? So let's take a look at elliptical galaxies. So elliptical galaxies, they have a smooth distribution of brightness from their very central part all the way to the extreme parts. So you see in this picture here, so we have this kind of a bright central area, and as you move away and then you observe and you take points in regions away from the bulge, the brightness diminish. And that diminishing brightness is pretty much smooth. It's not abrupt and does not change like in spirals. So how do stars in in elliptical galaxies behave? So stars in elliptical behave, they move in all possible directions. They don't go in a preferential direction like the stars that belong to a spiral galaxies. In fact, the stars, and I'm talking about the stars that happen to be in the spiral arms. So stars that happen to be in the spiral arms of spiral galaxies, they all go in the same direction because the spiral arms were formed out of a gas that flattened and was original rotating in a given direction, right? So elliptical galaxies are different. The stars in them are all kind of in all possible directions, and that's what these different arrows attempt to indicate. Now, if you look at the stars, they are part of spiral galaxies in the spiral arms. They all seem to be moving in the same direction, which is indicated by the yellow arrow in the right-hand side of the figure. So see, all of them are moving in a given direction, except the stars that belong to the bulge, to the central part. So the stars that belong to the bulge, to the central part, they seem to move in all possible directions. So they are bound to the center part of the galaxy. They are bound to the black hole that happen to be located in the very core, but they all move in all possible directions. So just by looking at the type of stars and their dynamics, you can tell the difference between a spiral and an elliptical galaxy. So in those are, let's take a look at features in a spiral galaxy. So spiral galaxies, they have cold gas, and if they have cold gas, star-forming regions are present, meaning you have baby stars all the time. You have H2 regions, you have OB stars being formed. In fact, the presence of OB, which are hot stars, the presence of OB stars in the spiral arms attests the newly formed region of stars. Now, when we study stellar evolution, we learn that massive stars evolve quickly, whereas low mass stars take much more time to complete their evolutionary cycle. So when giant molecular clouds, they happen to penetrate the spiral arms of galaxies, they undergo a short process of star formation. And in that star forming timeline, new OB stars are formed, and once they are formed, they light up the spiral arms. So we do see spiral arms in spiral galaxies because they are light up by the presence of OB associations or OB stars that provide the needed UV radiation to light up that region. And then astronomers can detect, and you can visually detect that. Now, in the region between spiral arms, you do have stars, you do have gas, but you do not have OB stars because they are dead. In that region, when the giant molecular clouds hosting these OB stars, when they happen to pass in the region between spiral arms, the OB stars are gone. they short-lived, and as a result, it doesn't have the flashlight, the UV radiation needed to light up that region. So you do have low mass stars, you do have gas, but you don't see it because there is not enough luminosity coming out of these regions. Now, elliptical galaxies can come in different sizes, in big size and small size, so they can be dwarfs and giants, um, as opposed to spiral galaxies. So in general, spiral galaxies have the same about size, 1,000 light years in dimension, as opposed to elliptical galaxies. So elliptical galaxies, they can be small, they can be big, so they can be dwarf and giant. So which indicates that maybe this giant, and that was one of the indications that giant elliptical galaxies might be the result of merge. First, they are found more easily in the core or in the central regions of rich clusters of galaxies, which indicates they might have been the result of several mergers. So which of these is not characteristics of elliptical galaxies? Stellar objects go in all directions. So this is one of the characteristics of elliptical galaxies. Oval shape, that's one of the characteristics. Active star formation, that is not a characteristic of elliptical galaxies. Dwarf and giant star is a characteristic of elliptical galaxies. And spiral galaxies, stellar orbits go in all directions. Well, in spiral, that is a complicated issue. And if we are talking about disk, they all go in all directions, but not in the bulge. In the bulge, they can take any particular direction. So let's keep reading. Disk shape, this is true for a spiral galaxy. Active star formation is true for spiral galaxies. And dwarf and giant types, that's not absolutely not true. They are always big. So I would say D is the answer, although you should be aware that answer A could be true if you look at the bulge. The bulge itself, the stars go in all possible directions. Let me keep going more. So spiral galaxies again. Spiral galaxies, they have this dust lane. See this darkness in between or right in the center that goes here and there. This dust lane is testify the presence of cold gas. Cold to the point that favors crystal formation. And this crystal, this dust, will deplete light from stars that happen to be in the background. So galaxies that happen to show this dust or dark dust lane indicates the presence of cold gas. And again, if there is cold gas in a certain environment, those are the proper conditions for star formation. So spiral galaxies have dust lanes, which means have cold gas, which means they might be forming baby stars. They are pretty much fertile. Now, what explains, what sort of theories, what sort of ideas we have to explain the rotation of galaxies? So exactly what goes on. So how can we explain spiral arms in spiral galaxies? So this diagram here, if you are following in your book, this diagram indicates the following thing. Well, if you take a disk distribution, right? So you have a central bulge and you have a disk that is homogeneous. It's all the same, all the way, very far away. And you allow now this system to rotate and apply Kepler's law, as we studied in chapter 3 or 4, which means part of the disk that is closer to the bulge, the central part, will rotate, will circle the central part with a speed that's larger than is in the outer skirts, in the outer regions of this disk. Which means if this is true, you will ended up with a situation that is shown in the fourth slide down, the fourth picture down. So you have the central part and you have a lot of wounded um, spiral arms around. And exactly, you don't observe that. What we observe is we have a central gauge, and out of it you have either a couple of spiral arms or you have four of them coming out of that region, but not as it is shown in there. So what's going on? And um, and one interesting solution to this conundrum was brought by, in fact, a very simple experiment done by a Russian. I think it was astronomer. Now I can't remember exactly. But what he did, he had a plate, a rotating dish with water. So if the dish is not rotating, put water and you drop a rock in the very center, you see the spread out of this wavelet in a circular fashion, right? So you can picture that. So you have a water, and then you throw a rock in there, and then you see these wavelets just spreading out in a circular way from the very central part. Now, if you add rotation to this dish, you observe spiral structure. And that brought the idea of one of the possible explanations of the spiral structure. It is the result of gravitational interaction of a galaxy with the neighboring galaxies. So think about the neighboring galaxies giving the punch, give the blow to the galaxy that rotates. And that transfer of energy spreads out. If you add rotation, you have these density waves streaming out of the central part. Now, when these density waves pass through the gas, you have contraction. You have a slow contraction of the gas in there. And this slow contraction triggers star formation. And when it triggers star formation, you have certain small percentage of OB stars being formed. And when the OB stars are formed, now you have the flashlight providing the ultraviolet radiation that excites the gas that allows astronomers to map this spiral structure. So basically, density waves is a very good explanation. And in fact, all the simulations that I'm showing before of spiral galaxies interacting among themselves, when they get close, the density waves is such that produce this nice spiral structure, and then you can see that highlight being formed. Now, the last point I would like to highlight is dark matter. So, when dark matter was first proposed in the 30th by Zwicky, he notes that compact group of galaxies, those that have a large number of galaxies but very close to one another, according to Newton's law, if you apply Newton's law and gravitational force to these galaxies, you wouldn't expect them to be bound. So you would expect them to be orbiting the common center of mass with such a speed they would be taken apart. They would pretty much disrupt and leave the cluster. And you don't see that. You see them preserved. So Zwicky proposed dark matter. He proposed there was some sort of material surrounding the cluster, this compact cluster, that would keep the observed and the seen galaxies together. Now, move to several decades further down in the line, add an improved technology to detect stars, position of stars, and and spectroscopy with high resolution spectroscopy, so you can measure Doppler effect with very good precision. And here's what you found. So based on what we see as far as visible stars in the galaxy, you would expect, like in the picture A, you would expect uh, so in fact the part A, it tells you the brightness, a brightness curve as you move away from the center. So the first slide in the very left hand part of the slide indicates the part of the galaxy that is the brightest one, is in the center part, and the brightness decreases. And again, we are talking about a spiral galaxy, right? So if you measure just by using Kepler's law, based on the number of stars that you happen to understand are visible in there, you would expect, as you see in the slide number 2, the rotational velocity of the star should fall the way it is shown in part C, which means after you move away from the bulge, right, which is the peak of in the slide C, in the figure C, the peak of it indicates that you are going away from the bulge. And now you are falling down as you move away, following the spiral arms as you move away towards the outskirts of the galaxy. You would expect the rotational velocity of galaxies would fall in a way we call Keplerian way. You would follow Kepler's law nicely. And what we observe is this doesn't happen. Look at slide D. The slide D show that fall doesn't occur. In fact, it flattens out, and stars that are further out or beyond away from the point we are, they tend to go around the center of the galaxy at a high speed. What is that? So I saw there were several attempts to solve for that. One was to parametricize Newton's gravitational law, putting a component that is not just the inverse of the distance squared for gravitational force. So you put another parameter that could take care of that. The problem is why you're doing that? You're doing that to fudge the data. So there is not a good explanation for that. But it can be done, and I saw there are some scientists that go that way. Another approach is to say, no, Newton's law, the F is equal gmm divided by r squared, is a good explanation of what's going on, and is symmetric with respect to magnetism and electricity and everything. So it's a good law, and besides symmetric, it's beautiful. So that's nice. But if you conceive, like Zwick did in the 30th, that our galaxy is embedded, is in fact surrounded by an unseen distribution of mass, but it's not baryonic mass in the sense that it's formed of protons, neutrons, and electrons. It is something that has mass, so has kilograms, if you will. We don't see it and does not absorb light, because surrounds the galaxy but does not retrieve light that comes from faraway sources. So it's not like dust that causes reddening. So it's something else, and that is so-called dark matter. So it so happened that dark matter is quite significant. It amounts for, as far as our galaxy is concerned, it amounts for 90% or more of the material needed to explain the dynamics of stars in our galaxy. So stop and think about this. So we live in a galaxy that we see all these stars, right? We can measure them, we name them. I'm here in the observatory, we start observing them. Okay, great. But the major component is unseen, and we don't know what it is. There are candidates, they're called WIMPs, weakly interactive massive particles. And perhaps in the next few years, those WIMPs might be um, classified, might be identified, and then we might have a better understanding of what dark matter exactly is. So far, we have candidates, but they are not baryonic matter. They are not black holes. Black holes were proposed as being such, like the relics of the galaxy formations, a bunch of black holes surrounding the galaxy. So you would add up enough material for that. But the projects like Machos and others were not able to find them. So they are not there. It's not a compact object. Jupiter-sized material were found, but again, does not amount for the, the, the percentage of material that is needed to explain the dynamics of the galaxy. And also does not explain when we go out of our galaxy and we observe clusters of galaxies, um, um, the amount of material we observe is not enough to explain the dynamics of galaxies in compact clusters. And dark matter nicely explains that. But again, we don't know what it is. And with that, I will close this subject and call your attention to these 2 points. So, what is important on the process of measuring galaxies in general? So, this chapter is important as you are able to identify and to name and list the differences between elliptical and spiral galaxies and their stellar population. Remember, we had a discussion that was closed on Tuesday, I think, or it's going to be closed tonight, that has to do exactly with this. I mean, what is our Milky Way galaxy? And I'm trying to get you guys to explain what is this type of stellar population we have, what type of stars we have in the spiral arms of our galaxy, what type of stars we have in the bulge, what type of stars exist surrounding the black hole in the very core of our galaxy. And the stellar population is also different if you observe elliptical galaxies and if you observe irregular galaxies. They tend to be different. So, star population is one important issue when we try to understand galaxies and their morphology, first of all. Second important aspect is for galaxies of certain size, and I mean spiral galaxies in general or elliptical galaxies, not the dwarf, they all come with black holes in their very core, massive black holes. And these massive black holes happen to be formed and existed in there since the formation of the galaxy. Since galaxies were formed, the central part of the galaxies were the region where the concentration of material was the most. And then the first generation of stars came to be formed. The stars zoom went through their evolutionary process, exploded, formed a black hole in an environment that is pretty much rich and populated by mass. Mass fall in the hole, and then you start increasing its mass to the point of now billions solar mass black holes. So that is an important component, and more are being found connecting the black hole itself to the dynamic of stars in the bulge. So it seems the black hole is not something important to the center of the galaxy, but also to control the dynamics and of stars that exist in the bulge. And the third important aspect of this chapter is the one related to dark matter, the important component of our of the galaxies in general, and also clusters of galaxies. Now, tomorrow, which is Wednesday, I will go over Milky Way galaxy and give a overview of cosmology, which is probably the last subject of this chat room. So, what exactly cosmology? What our universe is? How do you think the universe came to exist and came to be what it is? And what sort of evidence we have in support of the claims we present to you, like the Big Bang theory as being the best theory there is to explain the wealth of data we have at hand. Never forget that in astronomy, we don't come up with crazy theories. everything we say is backed up by data, and data comes through light. So that's why we need telescopes like those you see right there. In fact, those are pretty much simple, but astronomers need a telescope to observe things. And more so for professional astronomers, they need telescope and detectors. So telescopes collect light, detectors take this energy and convert into numbers. And these numbers are then analyzed by astronomers, and then we make sense of what's going on in the region responsible for producing the type of radiation. And then we can develop models and ideas, and that's where there is a field of sometimes different models coming up to explain the data. But the last word is data. Data is evidence. It's not a alternative evidence. Well, alternative facts. That's what it is. We can create different theories to explain data. This is okay. This is good in science, and but we learned before that theories make prediction. So if you have two different theories, they will come up with different predictions. And then what you do, you submit money, a proposal, get money, and build technology so that you can prove that the predictions of your theories are met with observations. If it's not, your theory is not so good. If the other theory is able to meet their prediction, the theory is better. And that's how science works. There is not such a thing as an absolute truth in science. But science is not crazy because the universe is not crazy. Science is based on observations, creation of hypotheses and theories predict things, and we go after those things using technology. And it's a no-end process, which means science is always alive. It's not dead. I mean, once you find explanation to something, it doesn't mean the doors to innovation, doors to what is out there that we don't know are closed. I mean, history have shown that when we become very comfortable with a theory, nature comes and tell us, okay, something here, that aspect is not well understood, and then we have to develop, different ideas to explain what it is. Okay, I will see you mañana. Bye.